Sometimes when we graph a logarithmic function, when we work with a logarithmic function, it is difficult to find the correct values for our table. So I will work right here with the values that were given for the specific function on our worksheets. So the first thing that we see, if we want to graph this function, the first thing that we want to remember is that the vertical asymptote is going to be equal to x equals to -1. And the reason for that is that the vertical asymptote comes from the solution from the zero of the argument of the logarithm right here. So that's the first thing that we know. We expect the function, the logarithmic function, to be similar to any logarithmic function, similar to this curve right here, and it will converge to a vertical asymptote. And this vertical asymptote right here, we expect it to be equal to x equals to -1. So that's the first thing. Now, in our worksheet, we have specific values to plug in for the x, and we can work with these values, but these would create an issue for us because we need to approximate some logarithms, I'm sorry. So let's look at that. If you plug in the value 1/2 for x into your logarithm right here, you get log of 1/2 plus 1. And this is going to be the log of 3/2 of 1.5. This 1.5 is a beautiful number, but it is not a power of 2. This is equal to 1.5. And 1.5, again, it's not a power of 2. And this creates some issues. I'm going to break it down using a property that you don't know yet, but it doesn't matter. And I can tell you, think about me as the oracle, that I can tell you that this logarithm is going to be equal to the logarithm of 3 with base 2 minus the logarithm of 2 with base 2. Okay, so the logarithm of 2 with base 2, this logarithm right here, is going to be equal to 1. We know that. But what about the logarithm of 3 with base 2? Now, if we plug in same values right here, the values that were given to us for the x, again, in different rows of this table, we get strange logarithms. So, logarithm of 3 with base 2, logarithm of 5 with base 2, logarithm of 9 with base 2. And this creates an issue for us. And the issue is created because none of those numbers right here is a perfect power of 2. How do we approximate those numbers? That's the issue. How do we know what is the logarithm of 3 with base 2 is? Well, I can show you a relation of numbers and logarithms. So we know, let's put down on the line of real numbers the numbers that are equal to the perfect squares or to the perfect powers of 2. 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4. Well, as you can see right here, we are missing the number 3 because 3 is not a perfect power of 2. Well, it's not a perfect power of 2, but there will be some kind of rational number up here that if you set 2 to that rational number, to a fraction, then the logarithm will be equal to 3. But the question is, what is this ratio? What is this fraction that we have to enter here? Same way, 5 is not a perfect square, 6. 7 is not a perfect square, and when we get to 8, that is a perfect power of 2, 2 to the third, then we know that the logarithm of 8 is 3. Now, then if you look at the corresponding logarithms, you see the following. The logarithm of 8 is 3, right here. The logarithm of 4 is 2. The logarithm of 2 is 1. The logarithm of 1 is 0. Now, if you look at those numbers, you are getting again the line of real numbers, and there is a relation as you move on, you can imagine that as I continue with my numbers, I will be able to get some kind of, let's say, correspondence of the numbers right here. So if the logarithm of 4 is equal to 2 and the logarithm of 2 right here is equal to 1, then the logarithm of 3, that is this one, must be somewhere between 1 and 2. I don't know exactly what the number is. I can tell you what the number is. You can calculate it, and the number is this. Right here, 1.58. If you have a calculator, you can calculate it. If you don't have a calculator, it's going to be an issue. But the truth is that you can approximate that your number will be somewhere at 1.5. You may not be exact, but you have an idea of where the number will fall. So log of 5 with base 2 will be somewhere here. Log of 6 will be somewhere here. Log of 7 will be somewhere here. And the distance between 2 and 3, if you split it into 4 pieces, as you can see right here, then this must be around 2.25. This must be around 2.5. This, that is the log of 7 with base 2, must be around 2.75. So the whole point is that you can find some relations of where to expect your points. You can approximate the logarithms. That's the whole point here. So when you work with these type of numbers, you will not know exact numbers, but you should be able to approximate them with the following method. So for example, if I want to calculate the log with base 5, let's say of 26, I know that the log with base 5 of 25 is 2. Now 26 is a little bit higher than 25, so the logarithm will be a little bit higher than 2, let's say 2.1. This is how we approximate logarithms. So in order to solve this problem and to graph this initial function that I have right here, the g of x, what I need to do is to create a table of numbers, put them inside the table and get the corresponding values, the corresponding points that I get right here. The point that I have, the first point that I have is 1/2, comma negative 1.5. The next point is 1, comma negative 1. The next point is 2, comma negative 0.5. I would like you though to review and see how I have approximated the log of 3, for example, to be around 1/2. Why? Because the log of 2 is 1. The log of 4 is 2. 3 is between 2 and 4, so this means that the log will be between the two logs, that is 1 and 2, so around 1.5. In the same way, log of 5 is between log of 4, that is 2, and log of 8, that is 3. And it is closer to 4, so the number will be around 2.2 or 2.25. This is how I approximated the numbers that I have, and you can and you should try to work on those numbers yourself. Since these are approximations and they are not the exact numbers, your graph, if you put those points on your graph, they're not going to be exactly on the curve, but it doesn't matter. You have a good idea of where the curve is. Another thing that I want to remind you or tell you is that this symbol right here is the symbol of approximation. This means that the number that I get is not exactly negative 0.5, but is around negative 0.5. So now I'm going to get those points and graph them on the actual graph, and I will also graph the function, connect those points all together, and use the x equals to -1 as my vertical asymptote in order to graph the specific function. So what you can see now on your graph is the approximations of the points that we just found in our table. And we can observe that those points seem to be on the same curve, maybe a little bit moved around. Maybe these points should be a little bit higher, so our approximation is not correct. Maybe we should put here another 5 and it goes a little bit higher. But pretty much the approximations are good and they give you a good idea of where the points are. Now, looking back to our function, we will go ahead and graph this function here. And this is going to be log with base 2 of x plus 1 minus 2. You can see that pretty much the points are in a good shape. We have all those points. And also, the vertical asymptote that we had, x equals to -1, is the vertical asymptote where the graph that we have converges to. Okay, so that's the graph of the function that we just given, log with base 2 of x plus 1 minus